everyone, Dr. Madi here, and today we're going to talk about forces and torques, aka wrenches in robotics. But before we begin, I want to thank each and every one of you for your support and for your feedback, and assure you that Mecharithm sees you as family, and together we're going to make robotics and mechatronics relatable, understandable, fun, and accessible to everyone. After this lesson, we'll be equipped with the tools necessary to express kinematics, statics, and dynamics for robots. So to celebrate this milestone, comment your questions underneath this video in the comment section, and I will personally answer each of your questions instead of my team. Comment your questions, and don't forget to like, share, and subscribe to be part of the Mecharithm family. So without further ado, let's get started.
A spatial force, generalized force, or a wrench is a six-vector consisting of moments and forces. Therefore, a wrench consists of a linear component or pure force and an angular component or pure moment acting at a point. If F is a linear force, the line of which is acting on a rigid body at a point R, and if we define a reference frame A, then, as we saw before, the point R can be represented in the reference frame A as RA, and the linear force in that reference frame can be represented as FA. Note that the point R may be a contact point if the force is applied by one of the fingers during, for example, robotic grasping, or it will be a different point if the force is due to an external load. You may refer to our previous lessons to understand how vectors and points are represented with respect to different coordinate frames. The linear force creates a torque or moment that can be represented as MA in the A frame and can be calculated as the cross product of the distance of the point of application of F to A and the force expressed in A frame. Note that the point of application of the force along its line of action is a material. Combining the moment of force into a single six-vector spatial force, we get the wrench expressed in the A frame as this equation. The three-vector FA shows the magnitudes of the forces in three directions that induce a three-vector torque or moment about the frame A. A wrench with a zero linear component is called the pure moment. Let's now see how we can change the frame of reference for a wrench. Values of the wrench vector depend on the coordinate frame in which the force and the moment are represented. We can represent the wrench in one frame in another frame if the homogeneous transformation matrix is known between the two frames. To learn more about homogeneous transformation matrices and how to calculate them, please refer to the lesson about homogeneous transformation matrices to express configurations in robotics. Physics tells us that power generated or dissipated by the wrench twist pair must be the same regardless of the frame in which it's represented. Note that the dot product of a spatial force and a twist is called power, and it's a coordinate-independent quantity. It means that it is the same whether the wrench and twist are represented in frame B or in frame A. We also know from the velocities and robotics lesson that the adjoint transformation can change the frame of reference for a twist. From the properties of matrix transpose, we can say that the transpose of the multiplication of matrices equals to the multiplication of the transpose of the second matrix and the transpose of the first matrix. Then we can write this equation based on the previous equations that we wrote. Given a wrench representation in frame A and in frame B, then the two representations are related by these equations. It means that the adjoint transformation changes the coordinate frame of the wrench from the frame B to the frame A and vice versa. Note that only the rotation matrix between the frames A and frame B is needed to change the coordinate frame of a moment from one reference frame to another, as you see in this equation. If we consider S to be the fixed or space frame and B to be the body frame, then we would have two ranges, the spatial range and the body range. Now let's see an example. Consider a robotic hand is holding an apple and there's a force torque sensor on the robot's wrist. We know the mass of the apple, direction of gravity, and the location of the apple in the hand. We want to find the forces and torques measured by the sensor. This figure shows a schematic of the problem. The force torque sensor measures the forces and torques in the F frame, and frame A is at the center of mass of the apple. We can write the forces and moments in frame A as this vector. Note that the moment vector is 0, since the force vector passes through the origin of the A frame and doesn't produce any moment there. mg is the force due to gravity, and it is in the opposite direction of the y-axis. To transform this range to the force sensor coordinate frame, we must calculate the adjoint transformation. And in order to calculate the adjoint transformation, we need the configuration of the force sensor frame relative to the apple frame. We can calculate that matrix as this matrix. Then, referring back to the velocities in robotics lesson, we can calculate the adjoint transformation as this matrix. The schizometric matrix representation of the position vector can be calculated by referring back to the exponential coordinates lesson as this matrix. Then the adjoint transformation can easily be written as this matrix. Finally, the representation of the range in the sensor coordinate frame can easily be calculated by matrix multiplication of the adjoint transformation and the representation of the range in the A frame. From this matrix, we can see that the range creates a moment of minus mgl about the z-axis of the F frame. Note that if more than one wrench acts on a rigid body, then the total wrench on the body is equal to the vector sum of the individual wrenches expressed in the same coordinate frame. Let's see this with two examples. Suppose that a robot hand is holding an apple subject to gravity. The apple mass is m1, the gravitational field is g, and the mass of the hand is m2. So note that here we also consider the hand's weight. We want to find the forces and torques measured by the 6-axis force-torque sensor. F is the force-torque sensor frame, H is the center of mass of the hand frame, and A is the center of mass of the apple frame. The gravitational range can be expressed in the hand coordinate frame H as this vector, and the gravitational range on the apple expressed in the apple coordinate frame A is this vector. The transformation matrices needed to calculate the adjoint transformation can easily be written as these matrices. I'm not going into details about how to calculate these matrices because the details of these matrices are discussed in the previous lessons on fundamentals of robotics. Then the range measured by the 6-axis force-torque sensor can be calculated as the vector sum of the individual ranges expressed in the same coordinate frame. The needed adjoint transformations can be calculated using these matrices. And finally, this vector shows the range measured by the 6-axis force-torque sensor. Let's see another example. Consider the multi-fingered grasping depicted in this figure. The goal is to determine the net effect of the forces applied at the contact points between the fingers and the object. In other words, we should map these forces to the body frame and add them as vectors. The schematic of the problem can be shown in this figure. FCI is the wrench exerted by the ice finger on the grasped object represented in the CI frame. the net wrench on the body to determine the net effective forces applied at the contact points between the fingers and the object in the body coordinate frame O can be found by the vector sum of the individual wrenches expressed in the same coordinate frame. Now let's see the final example. Suppose an arm-mounted mobile robot, X-Terrabot, is moving in a room and wants to pick up an object with body frame E with its end effector with the attached frame C. In the homogeneous transformation matrices lesson, we calculated the configuration of the object relative to the robot's end effector as the transformation matrix TCE. Please refer to that lesson to figure out how we got this matrix. Now suppose that the weight of the block that the robot should pick up is 1 kilogram. This means that the robot arm should provide approximately 10 Newton of force in the z direction of the block's coordinate frame E to compensate for the weight of the block. This force can be expressed as a wrench in the E frame. Now we want to express the same wrench in the end effector frame C. By definition that we saw in this lesson, we can write this equation. The transformation matrix TEC can be calculated by inverting the transformation matrix TCE. The transpose of the adjoint transformation can be calculated as this matrix, and thus the wrench in the end effector frame C can be calculated by matrix multiplication of the transpose of the adjoint transformation and the wrench in the E frame.
The software accompanying the textbook used to create these lessons includes very useful functions that you can use to calculate a lot of the things that we've learned thus far, such as inverse of a rotation matrix, screws, twists, the symmetric matrix representation of a vector, and a lot of other functions. To download the software along with the documentation, please refer to the written version of this lesson on the website. Since lesson 1, we have become familiarized with fundamentals necessary to represent motion and forces for robots and other mechanical systems. We are now equipped with the tools necessary to study kinematics, statics, and dynamics for robots. In the next lesson, we will start with learning about robot kinematics. Stay tuned. See you in the next lesson. Bye.